Okay, so you hear the word chemistry, and like most people probably think like, oh my gosh,
Hmm.
test tubes and bubbling beakers and like a whole lab, and it can be pretty intimidating.
It can.
But the truth is like chemistry is everywhere.
It is.
Like it's the study of everything around us.
Yeah.
It's like what stuff is made of and how it changes.
Yeah, exactly.
And that's what we're diving into today.
Absolutely.
Like literally everything. We're
Yeah.
going to break it all down.
Yeah, think of it as like a backstage pass to understanding like how the universe works at like the smallest level.
Yeah.
And the coolest thing is we're going to get into like all the fundamental building blocks of, well, everything.
Yeah.
And we've got a really great resource to help us do that.
Okay, what is that?
It's called S1, the Periodic Table and Chemical Reactions Revision Summary.pdf.
Oh, very nice.
And it's full of like essential ideas to get anyone started with chemistry.
Wait, so for someone who's totally new to chemistry,
Yeah.
this is going to be great.
Absolutely. And our goal isn't to turn you into a chemist like right away,
Right.
but to give you like that solid foundation and those light bulb moments where it all starts to click.
Yes, I love those moments.
They're the best.
Okay, so let's start at the very beginning.
Okay.
So the source is saying that literally everything around us
Mm-hmm.
is made up of these tiny things called atoms.
Tiny, tiny things.
Yeah, so the air we breathe, the chairs we're sitting on, even us.
Yeah, even us.
We're all made of atoms.
And they're so small you can't even see them.
Crazy.
Yeah, it's mind-blowing.
Okay, so these atoms, they come in different what they call flavors.
Flavors, yeah, it's a good way to think about it.
Okay, so different types.
Yeah,
And those different types are what we call elements.
precisely.
So each element is made of only one kind of atom. So it's like if you're building with Legos, but you can only use one type of brick.
I like that analogy.
Yeah.
So like hydrogen is all one type of atom, oxygen another, and so on.
Got it.
Yeah.
Okay, so all these different elements,
Yeah.
the source tells us there's 118.
118 that we know of.
Oh, wow.
Yeah.
Okay, they're all organized on this chart that we call the periodic table.
The periodic table, yes.
Yeah.
Have you seen it?
Oh, yeah.
Yeah.
I remember it from like high school chemistry class.
Yeah, it's iconic, right?
It is. It's like this big chart on the wall usually.
Exactly. And it's like the ultimate catalog of all the ingredients for literally everything.
Oh, wow. That's pretty cool.
It is.
So each of these elements has like his own little ID card.
Okay.
They have a name, like we've got hydrogen.
Yeah.
It's got a symbol, which is H. And then you've got helium, which is He.
Yes. And notice how we write those symbols.
Oh, yeah.
The first letter is always a capital letter.
Okay. And the second one, if it's there, is lowercase.
Exactly. It's like a universal code for chemists.
Okay, got it.
Yeah. And each element also has an atomic number.
What's that?
It's like a unique identifying number for each element.
Okay.
So for hydrogen, it's number 1. For helium, it's number 2, and so on.
Okay, so it's like their place in line.
Exactly.
Oh, that's cool. So
Yeah.
the source points out that these symbols can have 1, 2, or 3 letters, but that first one is always uppercase.
Right. Like I was saying, it's their own little code.
Got it.
Okay. So we've got the periodic table, this awesome chart of elements, but it's not just random.
Right.
There's a method to the madness.
What is it?
So it's organized into horizontal rows called periods.
Okay. Periods?
Yeah. And vertical columns called groups.
Okay. So rows and columns. Got it.
And this arrangement tells us a lot about how the elements behave.
Oh, wow. That's so cool how it's all organized.
Yeah, it's like a giant puzzle where everything fits together.
I love it.
Yeah, me too.
Okay, so the source is talking about some important distinctions between all the elements,
Okay.
so we can divide them into metals and nonmetals.
Right, those are 2 big categories.
Okay, and what's the difference?
Well, metals tend to be shiny. They conduct electricity and heat well.
Oh, okay, like a copper wire.
Yeah, exactly. Whereas nonmetals are usually dull. They don't conduct electricity or heat very well.
Oh, okay, like the wood of this table.
Exactly.
Okay, and then there's also solids, liquids, and gases.
Right. So think of iron, that's a solid at room temperature.
All right.
Mercury, that's a liquid at room temperature.
Oh, yeah, that's cool.
Yeah, it's the only metal that's liquid at room temperature.
Wow.
And then oxygen, that's a gas at room temperature.
Okay, so the periodic table shows us all these different states of matter.
It does, and it also shows us which elements are naturally occurring.
Oh, right, like they're found in nature.
Exactly, and which ones are man-made.
Man-made, so scientists made them in a lab.
Yeah, pretty cool, huh?
That is very cool.
Okay, so we've talked about periods, those rows, but let's talk about groups, those columns.
Okay,
The source says that elements in the same group have similar chemical properties.
so they kind of act alike.
Yeah, they react in similar ways, almost like they're chemical siblings.
I love that chemical sibling.
Yeah, so let's look at some examples. Group 1, the alkali metals.
Okay.
These are lithium, sodium, potassium.
Oh,
And they're all super reactive, like they'll burst into flames if you put them in water.
whoa, that's crazy.
I know, right? Then there's group 7, the halogens.
The halogens.
Yeah, fluorine, chlorine, bromine.
Okay.
These are also really reactive, but in a different way.
Okay, how so?
They like to bond with other elements to form compounds.
Okay, so they're not as dramatic as the alkali metals.
No, not quite as explosive, but still very reactive.
Got it.
And then there's group 8, the noble gases.
The noble gases, those sound fancy.
They do, right? These are helium, neon, argon.
Okay.
And these guys are like the cool kids of the periodic table.
Oh, why is that?
They don't really react with anyone. They're very stable and happy on their own.
Oh, okay, so they're like the introverts of the periodic table.
Yeah, you could say that.
Okay, so understanding these groups can help us predict how an element might behave.
Exactly. It gives us a good starting point.
That's really helpful.
Okay, so we've been talking about individual elements, but what happens when they start hanging out with each other?
Yeah, what happens then?
This is where we get into mixtures and compounds.
Okay, I've heard of those before, but I'm not sure I totally get the difference.
Okay, well, let me explain.
Okay.
Imagine you have a bowl of candy,
Okay, I like where this is going.
and there are all different kinds of candy in the bowl.
Mm-hmm.
That's kind of like a mixture.
Right.
You've got different things all mixed together, but they're not actually connected.
Okay.
In chemistry terms, the mixture is when you have different elements or compounds that are physically combined but not chemically joined.
Oh, okay, so they're just hanging out together.
Exactly. They haven't formed any strong bonds.
Okay, so like sand and sugar mixed together.
Yeah, perfect example.
They're still sand and sugar even though they're mixed.
Exactly. And you can usually separate them pretty easily.
Oh, right. You could just like pick out the sugar or something.
Well, you could, but there are better ways.
Okay, like what?
You could add water to dissolve the sugar.
Oh, and then the sand would be left behind.
Exactly. And then you could filter the sandy water to separate the sand from the water.
Oh, okay. That makes sense.
So mixtures retain their individual properties and can be separated by physical means.
Okay, got it.
Now, a compound is different.
Okay. So,
Think of those candies in the bowl, but instead of just mixing them, you melt them all down and make a whole new type of candy.
oh, okay.
So a compound is two or more elements that have chemically joined together through a chemical reaction.
So it's like they've gotten married and become one.
Exactly. They've formed a strong bond and created something new.
Okay, and the source is saying that compounds are not easy to separate.
Right. You can't just filter them or evaporate them back into their original elements.
So you need like a special tool to break them apart.
Yeah, you could use a process called electrolysis.
Electrolysis.
Yeah, it uses electricity to break the chemical bonds.
Wow, that's intense.
It is.
Okay, so compounds are formed through a chemical reaction.
Exactly.
And mixtures are just physically mixed together? Okay, I think I finally understand the difference.
Yeah.
Now, what about chemical reactions? We talked about them a little bit, but what exactly are they?
So a chemical reaction is basically a process where reactants, which are the starting materials,
Right.
transform into products, which are new substances.
Okay, so it's like ingredients turning into a cake.
Yeah, that's a good way to think about it.
Okay,
Yeah.
so how do we know if a chemical reaction has happened?
Well, the source gives us some telltale signs.
Okay.
So the first one is a change in color.
Oh, okay, so like when a banana ripens and turns brown.
Exactly. That's a chemical reaction happening.
Okay, cool.
What else? Another sign is a change in temperature.
Oh, okay, so like if something gets hot or cold.
Right. Some reactions release heat and some absorb heat.
So like if you mix two chemicals together and they get really hot.
Yeah. That would be an exothermic reaction releasing heat.
Okay, and if they get cold?
That would be an endothermic reaction absorbing heat.
Okay, got it. What else?
Well, another sign is the production of gas bubbles.
Oh,
The source calls this effervescence.
effervescence. That sounds fancy.
It does, right? So think about when you shake up a soda bottle and it fizzes.
Yeah.
That's actually a physical change releasing dissolved gas.
Oh, okay.
But if you mix baking soda and vinegar and it fizzes,
Oh, yeah?
that's a chemical reaction producing new gas bubbles.
Okay, cool. What else?
Well, sometimes a solid will suddenly appear in a liquid mixture.
Oh,
This is called a precipitate.
a precipitate.
Yeah, it can look like the liquid is turning cloudy or forming tiny particles.
Okay.
And lastly, some reactions release energy in other forms, like light or sound.
Oh, okay, so like fireworks?
Yeah, fireworks are a great example of a chemical reaction releasing light and sound.
Wow, chemistry is so cool.
It is.
Okay, so we've got chemical reactions where new things are formed, but then there's also physical changes.
Right, and it's important to distinguish between the two.
Okay, so what's a physical change?
It's a change where no new substances are formed.
Okay, so it's the same stuff just in a different form. So like if I tear a piece of paper in half,
Yeah, that's a physical change.
it's still paper, just in smaller pieces.
Exactly. And a classic example is changes of state.
Changes of state.
Yeah, so like when ice melts into water.
Oh, okay, or when water boils and turns into steam.
Exactly. It's still water, H2O, just in a different form.
Okay, got it.
Dissolving sugar in water is also usually a physical change
Okay, why is that?
because the sugar molecules are just spreading out among the water molecules. They're not chemically bonding with the water.
Oh, okay.
So you can get the sugar back by evaporating the water.
Okay, so chemical changes are all about making something new, and physical changes are just about changing how something looks or feels.
Exactly.
Got it.
Okay, so the last thing the source talks about is the rate of reaction.
The rate of reaction. Okay, what is that?
It's basically how fast a reaction happens.
Okay.
And understanding this is super important in all sorts of fields.
Okay, like what?
Well, in industrial chemistry, you want to produce materials efficiently, and even in things like cooking and food preservation.
Oh, okay. I never thought about it that way.
Yeah, it's all about chemistry.
Okay, so what are some factors that affect the rate of reaction?
Well, one key factor is particle size.
Particle size, okay.
Yeah, so if you break down a solid reactant into smaller pieces, you increase its surface area.
Okay.
And this increased surface area means the reaction will happen faster.
Why is that?
Well, think about lighting a pile of logs versus a pile of wood shavings.
Okay.
The shavings will catch fire much faster because there's more surface area exposed to the oxygen.
Oh, that makes sense.
Yeah, so the more finely divided the reactants are, the faster the reaction.
Okay, got it.
And another key factor is temperature.
Temperature.
Yeah, generally if you increase the temperature of a reaction mixture, the reaction will go faster.
Okay, why is that?
Well, heat makes the particles move around faster.
Okay.
And when they're moving faster, they're more likely to collide with each other.
Oh, okay.
And those collisions are what cause the reaction to happen.
Okay, so
Yeah.
smaller pieces and higher temperatures mean faster reactions.
Exactly.
Okay, that's good to know.
So we've covered a ton of information today about elements. The periodic table, compounds, mixtures, chemical reactions, and even the rate of reaction.
That is a lot.
Yeah, we've gone from the smallest building blocks to the processes that govern how things change.
So with this new knowledge, start looking around you and try to identify what's a mixture and what's a compound.
Yeah, like, is your coffee a mixture or a compound? I'm not sure.
It's a fun little challenge.
I like it.
The world is full of chemistry once you start looking for it.
Yeah, it's like a whole new way of seeing things.
Absolutely.
Well, thanks for joining us for this deep dive into the fundamentals of chemistry.
It's been my pleasure.
And until next time, keep those chemical concepts in mind.
And keep exploring the fascinating world around you.
See you next time.
Bye.
Bye.